Well, welcome to RTBLive. I'm Hugh Ross, the president and founder of Reasons to Believe. I've got a talk prepared for you today. Uh, but for all of you fathers out there, we had a great Father's Day this past Sunday. And one thing I haven't told very many people about, but my two sons claim that I'm infamous for my dad jokes. In fact, when they were in their early teens, they would get all their friends together and say, "Dad, please tell them one of your bad jokes," and then tell them another one. So what I got for Father's Day as a gift was this book, 160 of the worst dad jokes. So now I'm really equipped to annoy my two sons and my daughter-in-law. So, and many of you want to know where you can get this, I'll be happy to pass that on to you. If any of you really have a need to annoy your children, this is really the best tool that's out there. Now, I've prepared a couple of talks for RTBLive, one on the faint sun paradox and one on my new book, Weathering Climate Change. So I'm going to speak about, well, I'll tell you, a question I frequently get, both on Facebook and Twitter, and in my speaking events too, when we had them, was what is the best argument against a naturalistic theory for the origin and history of life? And there's several really good evidences that establish that there needs to be supernatural, super intelligent, frequent interventions to explain the origin and history of life. But one thing I've found engaging evolutionary biologists is a thing that is almost never taken into account is the changing physics of the sun, the earth, and the moon. It's the changing physics of the sun that plays the best role. So this is an abbreviated version of the normal talk I give on the history of the sun and how it challenges naturalistic evolutionary models. I'm going to speak for about 30 minutes, then we'll take the rest of the time for questions, whatever questions that you care to raise. So you can be thinking about that. And so, and let me start this. And actually, I've got an assistant that will be moving the slides. And this opening slide just simply shows you how you can connect with us. If you don't get to ask your question today and don't get an answer, all of our scholars at Reasons to Believe do answer questions both on Facebook and Twitter. And we do have a 24/7 YouTube channel, and the videos are being uploaded frequently on that channel. And you can subscribe. It's free to subscribe, and you'll be alerted to all the new videos that are available. And if you want my slides for today, you can get those slides. You can get them. You can download them for free by going to reasons.org/Ross. And if you do that, you'll be able to get the relevant chapter of Improbable Planet. I think it's chapter 12 that we're giving away for free at the same URL, reasons.org/Ross. So if you want to dive deeper into the faint sun paradox and how the implications it has for the history of life on planet Earth, you can get that free chapter from Improbable Planet. And one of the things I've found interesting as this book, Weathering Climate Change, has got released, and once again, you can get a free chapter at reasons.org. By the way, you can get lots of free resources by going to reasons.org/Ross. But I've been running into a lot of skeptics of global warming and climate change. And the skepticism is basically based on the fact, there was a whole lot more carbon dioxide and methane in Earth's atmosphere when life was first appearing on planet Earth, and the temperature was fine. So isn't all this stuff about global warming and blaming it on carbon dioxide and methane completely bogus? What they're not taking into account is that the sun was much dimmer at the origin of life than it is today. And it's only thanks to the fact that Earth had way more greenhouse gases back then than it's got now that life was able to survive on the planet Earth. So with that, let me jump in to the talk today, The Faint Sun Paradox, subtitle, New Evidence for Creation, New Evidence for Special Creation. And as I've already mentioned, naturalistic models for life's origin and history only consider the life sciences data. They fail to consider the simple sciences, the physical sciences, and in particular, the role of the changing physics of the sun, the earth, and the moon. And scientific models that provably lack explanatory power or are judged to be failed models. And my whole point here is the reason why so much of our society and our scientific community really believes that the origin and history of life can be explained by strictly naturalistic processes. They've not expanded the scope and explanatory power to include all the scientific disciplines. It's not enough to look at evolutionary biology or the fossil record. One must look at all the sciences because, after all, the history of life is an interdisciplinary study. And my background is as an astronomer. I studied galaxies and quasars, but I also had a lot of training in stellar physics. And one of the things we notice is that all stars flare. And stars, as they age, flare less, and they reach a point where they start to flare more. Often I remind audiences that stars are a lot like human beings. They're quite unstable when they're very young, and quite unstable when they're very old, and they're maximally stable when they're middle aged. In the case of stars, it's much more extreme. They're only stable when they're exactly halfway through the nuclear burning history of fusing hydrogen into helium. And in this particular slide, you get to see the flaring activity of the sun over its 9 billion year nuclear burning history, where it's fusing hydrogen into helium. And the y-axis there is logarithmic. The flaring activity of our star, the sun, when it was just formed, was about 1,000,000 times higher than it is today. And what we see there is that the flaring activity of the sun gradually drops as it ages. It hits a minimum when it's 4.57 billion years old. That's where it is right now. And as we go into the future, the flaring activity will pick up. It won't go as high as a factor as 1,000,000 above where it was when it was young, but it will get into the factors of tens of thousands of higher than where it is right now. But the whole point is we are living at the ideal moment in the history of the sun where the flaring activity, the only time in the sun's history where the flaring activity has been low enough for us human beings to be able to exist, thrive, and develop global civilization. And what we now know is that this minimum flaring happens when the sun is 4.57 billion years old. We also know that there's a brief window of extreme luminosity stability that lasts about 100,000 years. In fact, I got a blog coming out this Monday, which is going to talk about a brand new study just published where they've compared the flaring activity of the sun with 369 stars that come the closest to matching the characteristics of the sun. What you see there is that they flare a whole lot more than the sun at levels that would be damaging for human civilization. But a second thing that they bring out, and I actually show you graphs in this article will be coming out, is that when you look at the luminosity variability of these most sun-like stars, the luminosity variability is 5 times higher than we see in the sun. So we're literally orbiting the only star that we know that has sufficient luminosity stability to permit the existence of human civilization and to permit a population of billions of us humans existing on the earth. And from a biblical perspective, it's God's intent to bring an uncountable number of human beings to salvation into a redemptive relationship where they receive eternal life. And you actually see that in the book of Revelation, where he's going to bring an uncountable number. And the Greeks could count up to 1,000,000,000. So we're talking billions of human beings. Now, the key part, this is the one slide I really want you to remember. And if you download it, feel free to use it. It's a slide that I created. So I don't have any restrictions on its use. But it shows you the brightness of the sun throughout its history. And when the sun first forms, it's rapidly accumulating mass. And the brightness of a star goes up with almost a fourth power of the mass of the star. So in its accumulating mass, it brightens dramatically very quickly, gets about twice as bright as it is right now. Then it stops accumulating mass and goes through a brief period of about a half billion years where it slowly loses mass. And when it slowly loses mass, its luminosity drops, and then the sun ignites nuclear fusion. In the core of the sun, it begins to fuse hydrogen into helium. Basically, it's a gigantic hydrogen bomb. And once that fusion is efficiently ignited, from that point onward, the sun gets progressively brighter and brighter. And the reason why is that helium is denser than hydrogen. And so as the sun fuses hydrogen to helium, the density of the sun's nuclear furnace slowly rises. And the efficiency with which that nuclear furnace runs depends on the core density of the sun. So that explains why the sun today is about 20 to 23% brighter now than it was at the origin of life 3.8 billion years ago. And this is really the key of the message today, is that all stars, this is true of all stars, that once they ignite their nuclear reaction, that star from that point onward gets brighter and brighter until it runs out of fuel. Now, here's a challenge for evolution, is that with the sun getting brighter and getting brighter by more than 20% over the history of life on planet Earth, is that life on planet Earth cannot tolerate a change in the solar incident radiation on the surface of the Earth. And so, for example, if the solar luminosity were to drop 2% from where it is today, that would drop the temperature of the surface of the Earth sufficiently that you would get a runaway glaciation. A runaway glaciation is where you get a temperature drop, and when that happens, more of the precipitation falls as snow as opposed to rain. And snow reflects sunlight much more efficiently than liquid water. The comparison is 60% relative to 6%. So it's a very efficient way of reflecting sunlight away from the Earth. And when that happens, it drops the surface temperature of the Earth even more, which causes more snow to fall, more snow to accumulate. And in a very short period of time, the entire surface of the Earth becomes covered with snow that transforms to ice. Earth becomes a permanent ice ball, and that eliminates the possibility of life from that point onward. Conversely, if the solar luminosity were to increase by 4%, that would guarantee a runaway evaporation of all Earth's water. Actually, it could happen with just 1%, but 4% will guarantee that will happen. And what occurs here is that with that much of an increase, the surface temperature of the Earth would go up. When that goes up, it evaporates more water, and water vapor is an efficient greenhouse gas. It traps more heat from the sun, which raises the surface temperature of the Earth, which causes more liquid water and ice to become water vapor, which traps more heat, and you get this runaway, which very quickly causes Earth to lose all of its water to interplanetary space, because the solar radiation will break up the water vapor at a slow rate. And so that leads to an interesting paradox. How is it that the temperature of the surface of the Earth remained at the optimal level for life throughout the past 3.8 billion years? And what you'll see in chapter 12 of Improbable Planet is that over about a 60-year period, physicists and astronomers and geologists came up with 15 different ways you could compensate for the increasing brightness of the sun so the temperature of the Earth would remain optimal for life. And these are 15 non-biological. So I want to make it clear, I'm not just critiquing the life sciences for failing to take into account what's going on in the physical sciences. I'm also critiquing physical scientists for not looking at the life science. That's, to me, what was intriguing. Reading the scientific literature by physicists and astronomers, trying to find some way to resolve the fainter, younger sun so life could remain on the planet for 3.8 billion years. But it took several decades before they were willing to look at anything other than physical compensating factors. The truth is the biological factors are far more important than the physical factors. But what I'm going to do is give you a list, and I'm not going to spend a lot of time on this. If you want the details, you can get this in Improbable Planet. But these are the 15 compensating factors that were suggested in the scientific literature over a 50-year period on how it is, with the sun getting brighter and brighter, the temperature at the surface of the earth could remain optimal for life, so life could exist here for 3.8 billion years. And the first things that were suggested, this goes all the way back to the early career of Carl Sagan. He published a paper in Science where he said, well, if the early Earth had a lot more carbon dioxide and a lot more methane, those are powerful greenhouse gases, that would trap enough heat from the sun. So even with a dim sun, we could have warm temperatures on the surface of the Earth. And later a paper was published saying nitrogen is not a greenhouse gas, but it actually enhances the efficiency of carbon dioxide and methane to operate as greenhouse gases. So those were suggested, but papers were published making the point there's really no way the early Earth could have sufficient carbon dioxide, methane, and nitrogen to actually compensate for the much dimmer sun. So papers were published basically making this point that if you got a lot more volcanic activity, and we do know there was more volcanic activity billions of years ago, this would cause a greater release of carbon dioxide and nitrogen that would help. You would get a lot more. Well, they're also saying maybe the volcanoes back then were different, where they didn't release as much ash and aerosols, because those actually would block out the light of the sun. So they were suggesting a difference in volcanoes. They were saying maybe the Earth was a lot darker. Maybe the Earth was like the moon, very dark surface, and with a darker surface, it would absorb more sunlight. The problem with that is we know billions of years ago, the Earth was mostly covered with water, and at one point totally covered with water. So it couldn't have had a lower albedo. And then they suggested, well, maybe cryptogamic soils. This is really the only biological solution that was proposed. Cryptogamic soils are very dark, and they existed billions of years ago. These are basically microbial colonies, symbiotic colonies, and they produce a very dark surface that would help lower the albedo. But that only works if you got a lot of continental landmass. And that's the other problem. Past continents might have been at higher latitudes, and you got less reflectivity. Let me just go through the rest of this list. A faster rotation period would help. And if you got a lower cosmic ray flux and lower past interstellar dust, that means more sunlight can get through to the surface of the Earth. And a couple of my astronomer friends at Caltech published a couple of papers where they said, maybe we were wrong about the initial mass of the sun when it ignited nuclear fusion. If its mass was 5% greater than it is today, that would allow the sun to be quite a bit brighter. Because Carl Sagan was claiming that the sun was 30 to 35% dimmer at the origin of life. And these two Caltech astronomers basically said, not so fast. We could actually have it as small as 18% dimmer rather than 30 or 35%. Now, what I wrote about in Improbable Planet, these 15 factors indeed all play a role, but they all play relatively minor roles. And it is true that almost all of these 15 play some role in compensating for the dimmer sun. However, the biggest role is played by life on planet Earth. Different life at different times is really the key to resolving how you can have life abundant on planet Earth for 3.8 billion years, in spite of the fact that you've got the sun much dimmer than it is today. Just right life on Earth at just right times is the major compensating factor for the sun's increasing brightness that explains why the temperature on the surface of the Earth was optimal for life for 3.8 billion years. Now, we do know chemically that the most important reaction that compensates for the brightening of the sun is the silicate-carbonate reaction. And this is the only equation that's going to be in my talk. And I'm just going to show it to you. You don't have to really understand it. For all of you chemists out there, you can look at the top two lines. The rest of you, just look at the bottom line. Continental land masses are made up of silicates. A silicate is silicon with 3 oxygen atoms attached to it. And so in this example, I'm showing you calcium silicate, but this also works with any other metal, magnesium, iron, whatever. And the continental land masses are basically made up of all these metal silicates. And when you get exposed, this doesn't happen when all you got is oceans, but once the continents appear, this really explains why it's so crucial that our planet have a combination of surface oceans and surface continents. This reaction only works on a planet that's got substantial amount of its surface covered by oceans and a substantial portion covered by continents. That's one of the reasons why I'm confident that planets like Earth are extremely rare in the universe, because if you want life to exist for a long period of time, a fundamental requirement, this reaction must work. And so what you're seeing here is that if you got a water cycle, and again, this only works if you got a water cycle where liquid drops of water are falling on continental land masses. And those liquid drops of falling water act as a catalyst. They don't factor into the net reaction, but they act as a catalyst to drive the reaction. Without rain, drops of liquid water falling on exposed silicates, this reaction will not run. But the net result is, thanks to falling rain, silicates react with atmospheric carbon dioxide to make carbonates and sand. Silicon dioxide is sand. And so you get this, here in this case, calcium carbonate and sand. But notice that carbon dioxide gets removed from the atmosphere. So this reaction can be sustained at the just right rates. You can be pulling this powerful greenhouse gas, carbon dioxide, out of the atmosphere at the just right rates throughout the past 3.8 billion years to perfectly compensate for the increasing luminosity of the sun. There's one other benefit. The silicates that make up the continental land masses are not a valuable mineral. They really have no significant industrial use other than to use them for making stone structures. But when this reaction runs, you get 2 valuable materials. You get carbonates and you get sand. And it's because of this reaction that we can build concrete structures all over our planet. Concrete requires sand and it requires carbonates. But this reaction ensures that we have sufficient carbonates in the crust of the earth and sufficient sand that we can build all these amazing buildings and freeways and other structures that require significant quantities of concrete. In fact, one thing that's driving global warming today is the fact that the nations of the world are harvesting these carbonates and sand at a rate that they've never done before. In fact, you may not be aware of this, but there's actually an industrial shortage of sand in the world. And we who live here in California, we're very carefully guarding our beaches, because there are Asians, for example, that love to come over here, harvest all the sand off of our beaches, and use it for their industrial projects in their countries. But so far, we've been able to fend that off. And after all, the Asians love to come here and enjoy our beaches. That's a motivating factor. But they're really desperate to try to come up with enough sand. And you think sand is very abundant on planet Earth? I mean, this photograph here just shows you how much of it exists in different parts of the world, but it's actually in short supply. Now, what ensures that this reaction runs at the just right rates at the just right times is life on planet Earth. And the problem here is you want the reaction to run rather weakly billions of years ago and very efficiently at the present. As the sun gets brighter and brighter, it's necessary that this reaction run at a greater and greater rate. And to compensate for a 23% increase in the luminosity of the sun, it's necessary over the past 3.8 billion years that this reaction run a factor of 4 more efficiently over the history of life on planet Earth. And so when life first appeared on Earth as bacterial mats, like you see, for example, in Yellowstone National Park, these mats have a very low efficiency rate about driving this silicate-carbonate reaction. They do enhance it, but they enhance it only slightly. But that's all you need. That's all you want, billions of years ago. And then as we move into about 3 billion years ago, we have these cryptogamic crusts. And this is basically a symbiotic colony of fungi and bacteria and algae on the first continental land masses that appeared on the Earth. And as this photograph shows, only a few places in the world where this still exists, basically in high mountain and tundra regions. This is a photo I took up in the Canadian high altitude mountains. And basically you can see here, number one, it reflects sunlight at a very low efficiency, so it absorbs a lot of sunlight, but also it's more efficient than the bacterial mats at the driving the silicate-carbonate cycle. Now, as we move close to the present, say about a 500 million years ago, this is when vascular plants appear for the first time. And vascular plants have the capacity to accelerate the silicate-carbonate cycle a factor of 2 more than any of the microbial life that previously existed on the planet Earth. Vascular plants have this capacity to penetrate the rock and the soil with roots and to pull minerals and water up to the vegetation that exists above the surface of the Earth. But it's those penetrating roots that actually expose more of the silicates to falling rain. They basically create cracks within the silicates, and this allows more falling rain to come into contact with the silicates and causes the reaction to run much more efficiently. And in the present, we have trees, not just vascular plants, but we got big trees, and particularly the conifers. They're the most common trees that exist on planet Earth today. These conifers are extremely efficient at penetrating silicates. This is an example of Cathedral Peak in the Yosemite National Park. And what you see here are these conifers growing in solid granite. I mean, this is a granite rock here, and they're able to, a seedling can fall. Oh, it looks like smooth granite, but immediately begins to draw these little tiny roots. The roots begin to grow. They're very strong and powerful, and they can literally split apart the solid granite, create cracks in it, and this allows a lot more falling rain to be exposed to the silicates. And if we wait long enough, these conifers will cover the entirety of this mountain. It's amazing the steep, smooth granite exposures that they're able to get a foothold on and literally begin to break up the silicate. Now, today, this silicate-carbonate reaction that's driven by just right life on planet Earth at just right time, that accounts for 80% of the drawdown of greenhouse gases from the atmosphere to compensate for the brightening of the sun. The other 20% comes from the burial of organic carbon. And again, this is regulated by life. Life grows, it grows rapidly. It begins to pull a lot of carbon out of the atmosphere to make organic matter. And then it dies. And we live on a planet with sufficient tectonic and erosion activity that when a lot of organic carbon is produced by dying plant material and to a lesser degree dying animal material, it can get buried. And when it gets buried, it loses contact with the atmosphere, and then that can be driven by plate tectonics down into the deep crust of the Earth and even into the mantle of the Earth. And actually, this pulling down of organic material and having it driven by plate tectonics into the mantle of the Earth actually plays a crucial role and making possible the sustaining of plate tectonics for a long period of time. So the combination of this erosion of organic material, dead organic material, and the silicate-carbonate reaction has perfectly compensated for the changing physics of the sun over the past 3.8 billion years. But in order for these two organically or life-driven processes to work, it requires aggressive plate tectonic activity. And that's one of the unique things of planet Earth. Planet Earth is unique in that it has sustained aggressive plate tectonics for almost 4 billion years. And long-lasting plate tectonics, paradoxically, requires photosynthetic life. Four things must be fine-tuned, and fine-tuned to an extraordinary degree for long-lasting plate tectonics to be possible. You need abundant, dense water at the plate boundaries, at tectonic plate boundaries. Not just any kind of water, but what they call class 6 liquid water. That actually establishes a chemical reaction where the rock material at the plate boundaries can be transformed into talc. That acts as a lubricant, which allows the plates to slide against one another. But what has been recently discovered is a crucial role of photosynthetic life. Photosynthetic life precipitates uranium. Then the erosion forces of the Earth actually bring that precipitated uranium into subduction zones. That provides the heat, which together with a class 6 water allows a chemical reaction to run that makes this talc. Now, in order for all this to work, you need powerful, enduring radioactivity. You need a planet that's super endowed with potassium and uranium and thorium in its core and its mantle. This provides the heat that drives the plate tectonic activity. And also, you need a powerful, enduring dynamo in the Earth's interior. And that is a second benefit, that it produces a strong magnetic field that protects us from deadly solar radiation and deadly cosmic radiation. But to quickly bring this to a close here, and this is again covered in much more detail in 4 chapters in Improbable Planet. I've basically spent time talking about how life governs the rate of the erosion of silicates to pull carbon dioxide out of the atmosphere, and how, thanks to erosion and plate tectonic activity, dead organic material it gets pulled into the interior of the Earth. And that's another way that greenhouse gases get removed from the atmosphere. What I didn't take the time to cover, but again, it's in the book, and I think it's something everyone can understand. Just right life on planet Earth actually has an influence on the cloud cover. And that's something that was in the 15 physical science ways of compensating for the sun. Altering the cloud cover alters the reflectivity of the planet. And so if you alter it just the right way, you can get more or less heat and light from the sun absorbed on the surface of the Earth. And light also can change the Earth's reflectivity. As you're probably well aware, some plant life is very dark and therefore absorbs heat from the sun. Others is highly reflective and reflects sunlight away. So again, by creating just the right life on planet Earth with just the right reflectivity, just right life that can alter the cloud cover in such a way as to further alter the reflectivity of the planet, and then regulating the silicates and regulating the burial of organic carbon. Doing all these at just the right rates at just the right time is really how we can understand how life has been abundant and diverse on planet Earth for 3.8 billion years in spite of the brightening of the sun. But it draws us to a conclusion. It takes someone with a mind who knows the future physics of the sun, the Earth, and the moon. I've not covered the changing physics of the Earth, but it does change. The moon has been spiraling away from the Earth, so that needs to be taken into account as well. Again, more details are in Improbable Planet. But the bottom line, some mindless naturalistic process is not going to know which life to be on planet Earth at just the right time, in just the right locations, at just the right abundance and diversity levels to be able to perfectly compensate for the changing physics of the sun. It literally takes someone who knows what that future physics is and someone who's got the power to ensure that life on planet Earth that no longer is appropriate for compensating for the changing physics of the sun, Earth, and moon gets removed from planet Earth and replaced with new life that it's at just the right level is able to pull more greenhouse gases out of the atmosphere. And so this actually explains why the fossil record looks the way it does, why we see these repeated episodes of mass extinction events quickly followed by mass speciation events. The mass extinction events, that's the operation of the Creator removing life from planet Earth that's not efficient enough at pulling these greenhouse gases out of the atmosphere and replacing it with new life forms that are at just the right level, sufficiently more efficient at pulling these greenhouse gases out of the atmosphere. And another major challenge to naturalistic evolution, what we see in the fossil record is each of these mass extinction events is quickly followed by a mass speciation event. There's not a long time delay, relatively short period of time where we see a mass speciation event, where you get tens of thousands to millions of new species all appearing on Earth at just the right time. But I think the real challenge to naturalistic evolution, the mass speciation event, is always optimal for what you need to compensate for the changing physics of the sun. Another major challenge with a mass speciation event, we see that the ecological relationships amongst the herbivores, the carnivores, the parasites, and the detritivores, they're optimized immediately. There's no time delay. Naturalistic evolution would predict significant time delays. That's not what we see. We see optimal ecological relationships immediately with each mass speciation event. But I think what surprised me when I first began to read the Bible said this first 3,000 years ago. King David, in writing Psalm 104, the longest and most detailed of the creation Psalms, said this in verse 29 and 30, referring to life on planet Earth, saying, "They die and return to the dust. When you send your spirit," referring to God's supernatural intervention, "they are created and renew the face of the earth." And the fossil record tells us that God has done this not only repeatedly, but at just the right tempo to compensate for the changing physics of the sun. Physicists years ago calculated, okay, to what degree do we need to replace life on planet Earth in order to keep up with the changing brightening of the sun? And the answer is you want to do it about every 30 to 35 million years. And that's exactly what we see in the fossil record. We get mass extinction events followed by mass speciation events on a regular basis about once every 30 to 35 million years. But then this testifies again, you need a mind that knows this future physics and who has the power to remove the just right life and replace it with the just right life so we can have life abundant and diverse on planet Earth literally for 3.8 billion years. And you say, why 3.8 billion years? Because God's intent all along was that he would have a planet on which billions of human beings can live and thrive and develop the civilization and the technology to take the good news of salvation to all the people groups of the world, not in millions of years, but in only thousands of years. For that to be possible, the crust of the earth has to be filled with a treasure chest of over 75 quadrillion tons of biodeposits. We humans are the beneficiaries of 3.8 billion years of life that has preceded us, life that has chemically transformed the planet into an optimal condition so we humans can live and thrive, but also provide us with all the biodeposits, the coal, the oil, the natural gas, the carbonates, the sand, the concentrated metals, and the limestones, the marbles, so we can launch and sustain civilization. And notice that that is timed at the ideal moment when the flaring activity and the X-ray and ultraviolet radiation from the sun is low enough that we can live and thrive and actually see billions of human beings be able to exist at one time, hear the gospel, and respond to that gospel. In close, I like to give Psalm 104, verse 24. How many are your works, O Lord, and wisdom you made them all. The earth is full of your creatures. Notice this creation psalm is saying that it was the Lord that was responsible for all these different life forms. It's not giving the credit to just naturalistic process. Or as it says in Isaiah 45:18, referring to God, he did not create it to be empty, but formed it to be inhabited, formed it to be filled with a great abundance and diversity of life. Again, you can read more in Improbable Planet and in Weathering Climate Change, and you can get free chapters of both books at reasons.org/Ross. That's also a place where you can get all the slides from today's talk and many other resources. And it's going to be 2 weeks from today before we have another Reasons to Believe live. This is when Krista Bontrager will be giving a talk on Christian unity. So 2 weeks from today, that will happen. And yeah, we're going to be transitioning to a Reasons to Believe message like this happening every 2 weeks. But again, you can subscribe to our YouTube channel, and you'll be notified of the next RTB Live. You'll be notified of all the videos that we'll be posting for you. So take advantage of that and become a subscriber to the Reasons to Believe YouTube channel. We're going to segue to questions, and I'm probably not going to get to all the questions. We've actually launched a special podcast. That podcast is one where we answer all the questions we didn't get to in RTB Live, and you can subscribe to that by going to the Reasons to Believe podcast. And that's available on virtually all podcast services. Reasons to Believe podcast, and you can actually watch or listen to answers to the questions, all the questions we receive at RTB Live. So this brings us to a close, and I'll now spend the rest of the time taking questions, and our team here at Reasons to Believe will be funneling your questions to me. So this to me is my favorite part, and hopefully it'll be your favorite part as well. Okay. I think they're telling me I'm supposed to. You want me to go to all the questions? Okay, I see them here. Okay, Timothy asks, I believe you have said that the Bible refers to about a dozen purposes for creation, aside from creating a home for humans. What are the other purposes? I've also heard that human civilization can only last a maximum of 41,000 years. What factors limit the window of time for civilization? Well, in terms of the dozen plus, there's more than a dozen purposes for God creating the universe and earth the way he did. I discuss those in some detail in my book, Why the Universe is the Way It Is. There's a chapter where I deal with that. But I'll give you a few that discuss that. Number one, we need to realize that God created two different species of intelligent life, human beings and angels. And it tells us in the New Testament, particularly the writings of the Apostle Paul, that, that the angels intently are observing us to learn about the grace of God. We humans get to experience the grace of God. The angels, because they've not sinned, the righteous angels, because they've not sinned, they have to learn about the grace of God through observation, not through direct experience. And so God designed the universe and earth in such a way that we and the universe can be a teaching tool for the angels. In addition to providing a home for human beings, I've argued in why the universe is the way it is, that perhaps the primary reason for God making the universe and the laws of physics the way they are is to be a tool in his hand, an efficient tool in his hand to eradicate evil and suffering once and for all, while at the same time, he's enhancing the free will capability of us human beings to experience and to express love. And that's what's unique about the Christian faith. It presents us with a two creation model, not just a one creation model, namely that God creates the universe to be a tool to eradicate evil and suffering once and for all. And once that happens, he will bring those humans that choose to enter into a relationship with God into a new creation where evil and suffering will never exist again. Say, why does it exist right now? Because God's goal is to eradicate evil and suffering while he enhances our free will capability to express and experience love, which means our will must be tested. So it was on purpose that God designed the earth in such a way that Satan could come into the Garden of Eden and tempt human beings and give us human beings the opportunity of being exposed to the most challenging tests in the context of evil that is possible, since Satan is the most powerful and most intelligent creature that God ever created. That's just a few. You'll find a whole bunch more in why the universe is the way it is. And as far as the maximum time window, I think this needs to be broken into two contexts. There's a maximum time window in which global human civilization can be sustained. That's really the theme of my book, Weathering Climate Change, that we need exceptionally stable climate stability in order to be able to sustain global high technology human civilization. And that's bound to come to an end. At most, it's going to come to an end within 14 or 1500 years. So that will bring an end to the current high technology, high standard of living global civilization we're experiencing today. Because once the climate becomes extremely unstable, like it's been previous to 9,000 years ago, for the past 2.5 million years previous to that, we live in an ice age cycle. That ice age cycle, with the exception of the past 9,000 years, has driven extreme climate instability. But we know humans were living during the last ice age. But we also know that they had a very small population level and they were not global. They were not able to develop high technology civilization because the climate was just far too unstable. Global mean temperatures jumping up and down by 12 degrees centigrade, 20 degrees Fahrenheit on timescales of just a few centuries, which basically eliminated the possibility of large scale cultivation, the production of a sufficiently abundant food supply, that a whole bunch of us could be set free to do engineering, science, art, and music. So that won't be the end of human existence, but it will be the end of global human civilization. Now, there will come to a time when even human existence will be impossible, but that won't happen for probably about another million years. I write about this. I have a whole chapter devoted to this in Weathering Climate Change, where I talk about all the different factors that will come into play in the relatively near future from an astronomical perspective that will bring about the end of human beings. The fact that the flaring activity of our star is going to go up, the luminosity will continue to increase. And when that luminosity increases, it's not going to be possible to pull enough greenhouse gases of the atmosphere to compensate for that increased solar luminosity without bringing an end to photosynthesis. A lot of people aren't aware that carbon dioxide is just barely above the minimum level to sustain efficient cultivation of crops. During the last ice age, it actually dropped below that level. And if the carbon dioxide level were to drop even 10 parts per million below where it was during the last ice age, that would be the end of us being able to produce any food crops. So again, this has serious consequences for human existence. But I list about a dozen other things that will bring about our end, but nothing to worry about for another 500,000 to 1 million years. And I'm quite confident that we're going to see the completion of billions of human beings coming into relationship with the creator of the universe before that time happens. And we've got the promise in the Bible that once we do indeed see that large number of humans from all people groups coming into relationship with Jesus Christ, that's when God will move humanity who chooses to spend eternity with him from this creation to the next creation. Okay, we got a question here from John concerning evolution. What are your thoughts about a hominid inbreeding with a human? Is there hard evidence for it? And is it a factual statement that Neanderthal DNA is in the human gene pool? What is a factual statement is that certain segments of the human population have more in common with Neanderthal DNA than other people groups. For example, Northern Europeans have more similarity with Neanderthal DNA than people who are sub-Saharan Africans. And so this has been cited as evidence that humans living in the same region as Neanderthals some 40 to 45,000 years ago were breeding with these Neanderthals. That explains why we have greater DNA similarity. I've read the papers. I would argue that there is evidence for this breeding in the genetics that we see of Neanderthals and humans. Personally, I don't see it as compelling evidence. It is evidence, but it's not compelling evidence. And I was entertained by a debate I heard between our staff biochemist, Fuzz Rana, and our physical anthropologist when she was alive, Sue Dykes. Sue was very skeptical about this evidence for inbreeding. Fuzz was saying, I'm 80% persuaded that it really did take place. But notice, it's nowhere near the 100% level or the 99% level. So it may have happened. There's evidence for it, but it's not compelling evidence that it did happen. And it's quite possible that the reason for the genetic similarity is that we have the same environmental pressures, both the Neanderthals and the humans were living in that area. Okay, a question from P. Weinbrenner. How can we get a 2% decrease or 4% increase? Asteroid or volcano causing ash? So I think that's a reference to what I said in my talk, that if we were to see a lowering of heat and coming from the sun to the surface of the earth by 2%, that would bring about a runaway glaciation. And how could that happen? Well, yeah, if you get enough volcanic ash being distributed over the earth, that would block out sunlight, perhaps to a degree of 2%, which would bring on an ice ball event. But that would take enormous volcanic activity. You would need super volcanoes all over the world for that to happen. And those volcanoes would have to keep erupting for a long period of time. Because if this only lasts for a few years, that would not be adequate to bring about a permanent ice ball event. And there are times in Earth's past history where 80% of the planet was covered with snow and ice, but was covered with snow and ice for a sufficiently brief period that the planet was able to recover, mainly because we have the plate tectonics and the volcanic activity bringing carbon dioxide back into the atmosphere, which caused more sunlight to be absorbed, which brought the temperature up high enough where all that ice and snow melted. So this has actually happened in the past history, although at no time was 100% of our planet covered over with snow and ice. So yeah, you get super volcanoes, but you need a whole lot of them and need to keep erupting for a long period of time. The thing about an asteroid is, yes, an asteroid could strike the Earth and throw up enough dust into the Earth's atmosphere to create a winter that would last several years, blocking out the light of the sun. That would substantially cool the planet. But typically with an asteroid, you get what's called a global winter that lasts only a few years. And so unless you got a whole bunch of asteroids hitting one after the other, that probably won't do it. Okay, question from Lester. How can plant activity deposit uranium deep into the earth to affect plate tectonics? I thought plate tectonics is due to uranium and thorium already found deep in the Earth. Well, the uranium and thorium that's deep in the Earth provides heat from the radioactive decay that drives the plate tectonic activity. But what assists is that you have these photosynthetic life forms. And as they engage in the photosynthetic reaction, they have the property that they facilitate the deposition of a surface uranium precipitates. After all, there is uranium in the crust of the Earth. I live here in California, and our soil here in California is richer in uranium than the prairies, for example. And so the plants here are processing more uranium than they do in other parts of the country. And actually, this facilitates the deposition of surface uranium minerals. And erosion basically draws those minerals into the subduction zones. And so what happens is these plants are growing, vegetation is growing, where they produce these uranium precipitates. Erosion brings them off the high elevation regions, drives them down into the oceans, where you got these subduction zones. And when they get to the subduction zones, they accumulate and provide an extra heat source. And this extra heat source, it causes this class 6 water to react with the silicates and make some talc, which actually facilitates the subduction. If you want the details, it is in Improbable Planet, along with citations to the papers that were published just a few years ago that brought this up. Okay, another question from John. That question's already been answered. And then Judy asks a question. Does the silicate-carbonate cycle play into desert formation? Well, there's a lot of sand in the deserts, and that sand does come from the silicate-carbonate reaction. But there's sand all over the Earth. So even in places where you've got a jungle, you'll see sand. So yes, it does play a role, but it doesn't mean that the silicate-carbonate cycle guarantees that deserts will form. That's more in line with what kind of precipitation you get. And so if the precipitation is low enough, you will get a desert. And because the silicate-carbonate cycle has been running for a long time, you will find a lot of sand in that desert. But as you're probably aware, different deserts have different quantities of sand. So it basically depends, how efficiently that reaction has been running in different places. And of course, there's tectonics moves the sand around. Okay, a question from Bob Clapper. Is shell formation part of the silicate-carbonate cycle? It is in the sense that the silicate-carbonate cycle produces carbonates, and ocean mollusks will take that dissolved carbonate in seawater and use that dissolved carbonate to make the seashells. And so, oysters and clams, crabs, they get their shells from the dissolved carbonates that are there in the oceans. And those dissolved carbonates are there because of the silicate-carbonate reaction running on the continental land masses and erosion pulling a lot of that material down into the ocean. Okay, a question from Ron Martin. Is it God's plan that we burn oil and natural gas and make cement to precipitate another extinction event that will include us all? Well, the Bible doesn't say that God's going to bring about the extinction of humanity. Rather, he's intent on bringing about the salvation of billions of human beings and preparation for taking them to a brand new creation. But there is concern that we're going to burn so many fossil fuels, make so much cement, that we're going to warm the planet to such a degree that we bring about a catastrophic reemergence of climate instability that will be the end of our ability to have billions of us enjoying high technology, civilization, and a significant wealth. Again, I take that on in the Weathering Climate Change, make the point that, if we continue in the path that we are on, of burning fossil fuels to the degree that we are, and making as much cement as we're doing, that will cause the temperature to go up. And I write about the fact how if we were to drive the temperature up, global mean temperature on planet Earth, by another 2 degrees centigrade, human activity in the past 70 years has brought it up 1 degree centigrade. That's not enough to bring on a catastrophe, but another 2 degrees very likely will, because what that will do is melt the summer polar ice cap. And when you melt the polar ice cap, you're going to get a lot more water vapor coming out of the Arctic, and that will fall as snow in Siberia and Canada and quickly bring on an ice age. And you'll see graphs in Weathering Climate Change where I show you the history of the ice age cycle and how when you come out of an ice age, the temperature rapidly rises to a peak about 2 or 3 degrees centigrade above where we are now. And when it hits that peak, we rapidly drop back into an ice age. And we see that consistently throughout the entire ice age cycle, except for the cycle we're in right now. It was thanks to a huge asteroid striking in northwest Greenland that we did not go up to the usual maximum. It brought about a dramatic cooling event that prevented us from going up to the normal maximum, and the launch of human civilization at just the right time counterbalanced the natural cooling events that have driven us into an ice age. And that really explains why we've had 9,000 years of extreme climate stability. But yeah, if we continue on the path we are right now, we're going to bring that event on. We'll have catastrophic consequences. Won't be the end of humanity, but it will be the end of our global civilization. But the book is filled with 2 chapters of things we can do that will stabilize the climate and benefit the ecology around the world, while at the same time it boosts the world economy and especially boosts the economy of the poorest people of the world. God has provided us with multiple win-win solutions. And one of my motivations for writing the book was to take the politics out of climate change. What's driving the politics is you got one political side saying that global warming is real, it's going to cause a catastrophe, and the only way to deal with it is if the peoples of the world engage in draconian economic sacrifices in order to stabilize the climate, failing to take into account that we human beings are fundamentally sinful, and therefore trying to motivate billions of people to lower their standard of living by a factor of 2 or 3 isn't going to work. We need to come up with solutions where we boost the world economy while at the same time we stabilize the climate. And that's a biblical principle. God told us that we human beings have been put in charge of the planet's resources to manage those resources for the benefit of all life, not just our benefit, but the benefit of all non-human life. In other words, from a biblical perspective, we're not going to be put between a rock and a hard place, where we're going to have to choose between our personal benefit and the benefit of the rest of the world's life. We can actually fulfill both. Okay, question from Beatty Mosjord. How much of human pollution causes climate change compared to the sun? Well, the sun is getting brighter, but it's getting brighter at a very, very slow rate. As I showed you in those graphs, it's taken 3.8 billion years for the sun to brighten by about 22 to 23%. And so in terms of the sun brightening the earth enough to make a significant difference, that's 1 to 3 million years off at a minimum. So we can ignore that. However, the sun does go through tiny cycles of variation, the sunspot cycle, which is basically 11 years. And that changes the amount of sunlight coming on the earth by about 0.1%. Again, not enough to significantly disturb the climate, but it does explain why surface temperature records do show an 11-period variation. It's just based on that tiny 0.1% change. So in that context, the consumption of fossil fuels, human activity, has a much more dramatic effect on the surface climate of the Earth than what's happening with the sun right now. And again, if you want details, you'll see a whole chapter on the impact of the sun and weathering climate change. Okay, this is the last question. And again, we're going to do a podcast where we take on the rest of your questions. So that will be coming. And if you go to Reasons to Believe podcasts, you'll be able to subscribe and listen to answers to the additional questions that we'll be taking. But let me answer this last question from Ron Martin. Is there a natural albedo adjustment that will compensate for our putting the plant trapped CO2 back in our atmosphere? Well, I do have a few pages in Weathering Climate Change where I talk about some rather grandiose proposals to actually reflect away enough sunlight that it compensates for human activity that is warming the climate. In other words, they're saying we can continue to burn fossil fuels at the rate we are. We can continue with all of our factory output. We can continue with all of our activity. All we need to do is put some kind of shield between us and the sun, and that will block out enough sunlight to compensate for increased human activity. And so, for example, there's experiments being conducted by people on the East Coast, as well as in China, where they're talking about putting huge quantities of aerosols in our atmosphere that will block out enough sunlight to compensate for the increased human industrial activity. And there's about a dozen other proposals that are like that. Some of the more exotic ones are actually talking about putting a huge shield in outer space that would be between us and the sun, where it could be regulated with some kind of rheostat to actually lower or increase the amount of sunlight that reaches the surface. As you can imagine, these proposals come at a very great cost. But there actually is technology available to do that. And also, there are people saying, well, we can continue to burn fossil fuels at the rate we are. We just need to equip our fossil burning plants with scrubbers that actually pull the carbon dioxide out of the gases released from fossil fuel burning and convert that carbon dioxide back into fossil fuels. Again, quite expensive. And so I do talk about this, but basically I'm recommending that we pursue solutions to climate change and global warming that rather than costing so much that it cripples the world economy, there are solutions that would boost the world economy. So we'll take the rest of the questions for the Reasons to Believe podcast. And once again, you can subscribe to the Reasons to Believe YouTube channel. That will keep you alerted to future Reasons to Believe lives. 2 weeks from today, Krista Bontrager will be giving a talk on creation unity. So with that, I'm going to say goodbye. But again, we'll take the rest of your questions and you get that on the podcast. Thank you for joining us.